Today's warm-up question is very similar to the one that you saw yesterday. In fact, if you read it, you should recognize some of the numbers. It says a 0.071 kilogram paper cup falls from a 0.78 meter high table. That's exactly how it started yesterday. It is moving at a speed of 2.93 meters per second when it hits the floor. That's new information from yesterday. Is air resistance present? And then how much energy is dissipated due to air resistance? So we're going to go over this question. Okay, and this one requires you to use some critical thinking to figure out how to approach it. There's a couple different ways to be able to answer at least the first part, the first question that you see here. Okay, now the number, there's a little bit less for that, for number 2, but in terms of being able to determine if air resistance is present based on this scenario, I'm going to solve it one way, I'm going to tell you about another way, and then we'll talk about the answer to number 2 as well before we get into our notes today over power. Power is the last topic for this unit, which makes it the last topic of the semester. We are almost done. Okay. So power notes and calculations in your homework will be the power problem set in MyOpenMath, as well as finishing up your RA. All right, so for the warm-up question, we're going to start by labeling the information we're given. We have a mass of 0.071 kilograms. We have an initial velocity of 0 meters per second. That's implied by it saying that it falls, so it's falling from rest is an implication of it being written that way, as opposed to being thrown or knocked off or something like that. We know that it's going to fall from the top of this table to the floor, which means its displacement will be negative 0.78 meters because it's going to fall down. It is moving at a speed of 2.93 meters per second when it hits the floor. We didn't have that number yesterday. In fact, we had to solve for how fast it would be going yesterday when there's no air resistance. Okay, this question though is asking us if there is air resistance. So now we don't know whether or not we have free fall. Okay, we know it's falling, but we don't know if there are other forces like air resistance. So we can't use the same acceleration we did yesterday, but we do know that the speed at the end, it is falling down, so I do want a negative in front of that, negative 2.93 meters per second. That's the information that we have, and we're trying to figure out if air resistance is present. Okay, and so I need to determine, or I need to start by thinking about my energy. I know that initially I don't have any, okay, because this cup is at rest, okay, and so I don't have any kinetic energy initially. Okay, however, as it falls, I'm of course going to be gaining kinetic energy, and so anytime I have a change in my kinetic energy, I know that there is a situation where I have work being done on my cup. So that means there are forces acting on it. What forces might be acting on my cup? Gravity, right? We had that one yesterday. Force of gravity is absolutely going to be acting on my cup, which means there will be work done by gravity on my cup. Okay, but the question wants to know, is there also air resistance? And so that could be another force that we have to figure out. And so we're going to solve for it. We're going to figure out if it's 0 or not, basically. Okay, but we need to first determine what our work done by gravity is so that we can then start to look at, do we have a net work that is different than that? Or is my net work exactly equal to that? Is there another force doing work on my cup, or is it just gravity? Okay, but in order for us to be able to figure that out, we first need to figure out what the work done by gravity is. And the equation for work is force times displacement. If we want to know work done by gravity specifically, it's force of gravity times displacement. Okay, I don't have the force of gravity given to me, but we have calculated force of gravity over and over and over again since our forces unit. We know, or you should know, that force of gravity is the weight of the cup. It's the mass times the acceleration due to gravity. So that's this, 0.071 times negative 9.8. That's how you find force of gravity. So if you're trying to determine work done by gravity or work done against gravity, you'll need to be able to find Fg. Okay, so again, this is mass times gravitational acceleration. That gives me a force of gravity, or a weight force, of negative 0.6958 newtons. So now I know how much force there is due to gravity, I can find the work done by gravity, because this force is acting on the cup for the entire displacement, the entire time that it's falling, that whole negative 0.78. Okay, that whole negative 0.78 meters. So here is my work done by gravity is equal to my force of gravity, which we just found, times my displacement, which was in the question. And when I multiply my force times my displacement, I get this number, 0.543 joules. And that should sound familiar as well because it was in our warm-up yesterday. That was our answer yesterday. Okay, but that is the work done by gravity. Okay, 0.543 joules. And that gravity is adding that energy to the cup because it goes from having no energy at all to having, or at least no kinetic energy at all, to having this motion energy because that gravity is making it speed up. Okay, again, another way to think about the fact that it's positive work is that the force and displacement are in the same direction. Gravity's force is downward, the displacement of the cup is also downward. Okay, and so we have positive work done by gravity. All right, so now we know the work done by gravity. Now we need to figure out if there's other work being done. In order for us to figure that out, we really need to go back to an energy transfer equation. We need to start by writing our own equation starting here. Initial energy of the cup plus net work done on the cup equals final energy of the cup. Initially, 0. No kinetic energy at all. Okay, but work done on the cup, I have this work done by gravity that we just found, and the question is there also work done by air resistance? So there's potentially two different things doing work. And remember, net work is the sum of those different works that are done. Okay, and then my final energy is kinetic because I have this motion just before it hits the floor. So I'm going to write it out like this. Sorry. My initial energy is 0. My net work is the sum of the work done by gravity plus the work done by air resistance. If there is any, it might end up being 0. We don't know. And we're going to set it equal to our final kinetic energy. Okay, but looking at the information I have over here, I don't have kinetic energy. I do, however, have a final velocity. So instead of leaving this as KE, let's substitute in the variables for it so that it looks like that. You'll notice I also substituted in the value for the work done by gravity that we found on the previous slide. Okay, so now I have my work done by gravity, 0.543, plus any work done by air resistance, might be 0, don't know, equals my final kinetic energy, which is 1/2 mv squared using that final velocity. Let's go ahead and plug in some numbers. If it so happens that my final kinetic energy is equal to the work done by gravity, then I'm going to get 0 for air resistance. Okay, but if they're not equal, then that means there has to be something else doing work. So that's what we're about to determine, and of course we'll be able to see it algebraically as well. If we substitute in our mass and our velocity at the end, now we have 1/2 times 0.071 times negative 2.93 squared. Again, that negative is going to go away when I square that. And this entire right-hand side ends up equaling 0.305, which means it's not equal to that work done by gravity, and therefore there must be something else doing work. And that's going to be our air resistance, and we can find it now by subtracting 0.543 from both sides. So 0.305 minus 0.543 gives me my work done by air resistance is negative 0.238 joules. Okay, so now we know that gravity does positive 0.543 joules of work. Air resistance does negative 0.238 joules of work. Okay, so the cup should be moving faster than it is the point. That air resistance is working against it. It's slowing it down. Okay, so our answer to the first question, is air resistance present, is yes. Okay, we just determined that there is air resistance doing work. We even have a number, which is the second question. How much energy is dissipated due to air resistance? Guys, if you know the work done by air resistance, you know the energy dissipated. That's the definition of that work, is the change in energy caused by that air resistance is going to be dissipated energy. When you have friction or air resistance or things that remove energy, you have energy that is lost or dissipated from your system. It's another way of asking that question. Okay, now, when you report your answer though, if I say how much energy is dissipated, you don't type the negative because it's implied. If I say dissipated, it's implied that it's lost. So you just need to type 0.238 joules. Okay, if I ask you for work done, you then need to type the negative because it's not implied anymore. Okay, are there any questions about the warm-up? I told you I would explain one other way that you could have answered the first question. Okay, so the first part was, is there air resistance present? And of course, you can do it this way. Alternatively, if that's the only thing I was asking you to do, you could use free fall calculations to figure out how fast it would be going at the end. That's actually what we did yesterday. The first part of yesterday's calculation was determining the final velocity of the cup right before it hit the ground, which happened to be 3.91 meters per second, and comparing it. Is it slower than that? It is, and this question is only 2.93. So the fact that it's slower than it should be means that there is another force acting on it. It's not just accelerating due to gravity. So that's another way to approach the question, is using those kinematic equations to figure out how fast it would be going if the only force was gravity, and then comparing that number. Okay, so again, there's more than one way. Maybe you think of another one. Doesn't mean it's wrong. Okay, but you just need to be able to answer questions like this one. Does anybody have a question about this or about any part of the warm-up? So guys, this question is, as I said, a little tricky. Okay, this is a little bit of a tricky question. I probably wouldn't ask you a question like this on your multiple choice section of your test because that's a lot of steps for a single multiple choice question. However, you could see something like that on a free response, or as I mentioned before, a bonus question. So it would probably be a good thing to look back at. Okay? If you were maybe interested in earning bonus points. Okay, something like this. All right. Let's get into today's notes. Yes, sir. Yes. Okay, today's notes are on power, which is the last topic of the unit. Power, definition, you might want to copy it down, is the rate at which work is done. It means we're looking at a work-time ratio. Okay, so in order for you to have power, that means that you have to have work being done. So the same criteria that applied whenever we were looking at what constituted work, you need to use that same criteria when you're looking at how to calculate your power. Okay, because if you don't have any work, you won't have any power. So if the thing ends up being whatever question you're solving, you end up determining you have zero work, you have zero power as well. Okay, the criteria that we looked at when we determined whether or not work was being done was, is there a force, and does that force cause the displacement or oppose the displacement of the object? Meaning that some portion of the force is parallel to that object's displacement. So that's the same criteria we're going to use here. Okay, so if I ask you, what is the power output of a man carrying a box? Your answer is going to be 0. Because we talked about the fact that carrying something is 0 work. Because in that case, my force and my displacement are perpendicular to each other. No portion is parallel. Okay, so you have to keep those things in mind as well that we learned when we went over work. The equation for power is work divided by time. So this is the formula down here. In order for you to plug into this equation, your time must be in seconds and your work must be in joules. Whenever you divide joules by seconds, you get a unit called a watt, which should sound familiar because you guys should be familiar with watts, primarily from light bulbs or microwaves, hair dryers, but things with power output. Most of the things you're familiar with are going to be due to electrical power output, which is fine. We'll talk about that more later on. But your unit here is the watt. The abbreviation for watt is a capital W, which sometimes is confusing for students because I don't want you to look at this equation and think this is watts in the equation. This is not watts, this is work. The unit you get at the end when you divide your work by your time, that's your watt. Okay, so please don't mix it up because I know that can be kind of confusing. Okay, watt is a unit, work is a variable. Okay, so let's take a look at some examples, starting with one similar to what we saw in our notes previously. This question says, if each barrel is moved from the ground up to the top of a 5-meter ramp in the times indicated, where is more work done and where is there more power? So think back to what you remember about work and what we just talked about with power. We're going to assume these are identical barrels and turn and talk to your neighbor and see if you guys can agree who does more work and who has more power. I'm going to give you 29 seconds to discuss. All right, guys, so who does more work? The same. Y'all saw a very similar scenario to this. Remember, if you're doing work, okay, he's in this case, he's working against something. He's lifting this barrel. So I don't really care how far forward he goes because the force, okay, there is kind of upward if you're talking about lifting something. And because they start at the ground and they both end up at the same spot, they both lifted it to the same height. Now, I will say this, the actual force used by this guy is less than the force used by this guy. Okay, the one that's pushing it up the ramp uses less force, but he has to push it a greater distance. So he still has the exact same amount of work as this guy who has to use more force, but he doesn't have to lift it as far. Okay, so it's a trade-off. We talked about that as well. But both of them do the same amount of work. Again, work is independent of the path taken. That's what we talked about like on the first day or second day of this unit. Okay, so they're the same. Okay, but what about power? There are two variables in that power equation. Work is one of them. The other is time. Who has more power here? The guy on the right. The guy who uses less time. Okay, because power is the rate at which you do the work. So if you do the work faster, you have more power, meaning if it takes you less time, you have more power. And that is true of this guy who is lifting because he does so in less time. Not because he's lifting, but because he does it in less time. Questions about that? All right. So let's look at some example calculations. This one says the weightlifter uses a force of 980 newtons to raise the barbell over her head in 5.21 seconds. Find her work. Okay, we talked about the fact that if you're lifting something, you have to be matching the force of gravity, matching the weight of that object, but they actually gave that number to us, so we don't have to figure it out. They told us that her force is 980 newtons. They gave us a time, which is not helpful if I'm trying to find work, because my work equation doesn't have time in it. It's just the force times the displacement. But the displacement's in the picture. Okay, and you might not be able to read it very well because it's a little smaller than everything else up here. But this picture shows she moves it from 0 to 2.04 meters. And so if I want to determine her work, I simply take her force from the question, 980 newtons, and I multiply it by the displacement, how far she lifts it upward, 2.04 meters. And when you multiply those numbers, you get work of 1,999.2 joules. Okay, so that would be her work. Okay, now, although I didn't need the time for that calculation, I do need it for this one. Find her power. Okay, so we've already found her work, 1,999.2 joules. In order for us to find power, we also need her time. That's in the question, 5.21 seconds. Power is work divided by time. Okay, pretty straightforward. We're just going to take those two numbers and divide them. 1,999.2 divided by 5.21 gives me a power output of 383.7 watts. Okay, so her power is 383.7 watts. And I don't have to write out the whole word watts. I could leave it as a W, but I'm writing it out because I don't want you to mix it up with work. Okay, once we get more used to it, maybe we'll just use the W. And in your MyUp Math, you do need to just use the W. I don't think it's in there typed out. All right, let's try this one. A 1994 Ford Mustang is driving down the road with a constant speed of 30 meters per second. The engine must exert a 5,000 Newton force to maintain this speed. What is the power rating of the engine? So this one's a little bit different because it's giving me a velocity. But guys, a velocity is really just a ratio of distance and time. If I'm going 30 meters per second, it means I go 30 meters in 1 second. It means I go 60 meters in 2 seconds. It means I go 90 meters in 3 seconds. And so I can get a distance and a time from that because that ratio will remain constant regardless of what distance I choose. Okay, it's always going to be 30 to 1. Okay, and so I've got now a distance and a time that I can use in my calculation, and my force is in the question, 5,000 newtons. Okay, and so from this information, if I want to find power, again, power is work divided by time, but I don't have the work. I do, however, have a force, and I do have a displacement, so I can find the work first using the F, my force times my displacement, F times D. 5,000 times 30 gives me a work of 150,000 joules. And then I can divide that by my time. My time in this case being that 1 second, because I'm really just looking at the ratio, 30 divided by 1. Okay, and so 150,000 joules divided by 1 second is 150,000 watts. A watt is a joule per second. Okay, so it's the same thing, joule per second or watt, but the standard unit is a watt. Now I will say this, we don't typically measure the power rating of engines and cars in watts. We use a different power unit. Does anybody happen to know? There it is, horsepower. I could ask you to do a conversion to horsepower. I'm not going to, but if you're curious and you want to look it up, you're welcome to. Okay. All right. I want to show you something here though, because this one was a little weird because I gave you a velocity. Well, there's actually a shorter way to solve this problem. If you look at these two equations, we're going to figure out what that way is. Okay, power is work divided by time. Work is force times distance. I could substitute this force times displacement into my power equation, which would make it look like this. Power is force times displacement over time. Does anybody looking at that equation see anything that you could do to simplify it? Anything that looks familiar in that formula? I know it's early.
In the top one?
Yeah, what? Anything up here that I could do to simplify it?
Just make it work instead of...
What is that?
Speed.
Speed. Okay, displacement over time would be more accurate. It's my fault for typing the D. Okay, but that's velocity. So I could simplify this equation by writing it like this. Force times velocity, because that's what it is. Force times distance over time is force times velocity. So if you have a question like the previous one, it's a lot shorter if you use this equation. However, I'm not going to give you this equation. You either have to memorize it, power equals force times velocity, or do what I just did and figure it out again if you forget it. But it's right here. Distance over time, there's my velocity times force. Okay, so if I use that equation instead, it's a lot faster to simply multiply my force, 5,000, times my velocity, 30, 150,000 watts. Don't have to do all the other steps. Okay, so you can do it either way, but obviously this is a little bit easier if you can derive that equation on your own or memorize it if you would prefer. Okay, so that is another formula for finding power. So we have power is work divided by time. We have power is force times displacement divided by time, or power is force times velocity. All right, let's try this one. If Miss Darwin does 3,066 joules of work when climbing the stairs at BHS and it takes her 1 minute and 20 seconds, what is her power output? I gave you my work and I gave you my time, but I gave you my time in a way that's not super useful. Please don't leave it as minutes and seconds. We need it just as seconds. So what is 1 minute and 20 seconds converted to seconds? 80 seconds. Okay, so that's going to be what I use for my time. So if I want to find my power, I already have my work, I already have my time. I'm just going to divide 3,066 divided by 80, and my power output would be 38.3 watts. And you can figure out your power output too if you want to climb up the stairs. Okay, in fact, I'm going to give you another one that's similar to some data that we maybe would have gathered if we had done this lab. It says, Thomas has a mass of 80 kilograms and climbs the same 4.16 meter stairs at BHS in 1 minute and 3 seconds. What is his power? Okay, so in this question, I've given you mass, I've given you the displacement or the distance upwards, since we're just going in one direction, and my time, 1 minute 3 seconds is going to be 63 seconds, okay, or Thomas's time. Okay, but if I want to find power, okay, I need work divided by time, and right now I don't have work, so I need to find the work first. Work is force times displacement. I don't have a force either. Again, we've talked about this a few times now, but if you are climbing stairs, climbing a ladder, or if you're lifting something up, the force that you have to use in order to climb, to lift yourself, or to lift anything up is equal to the force of gravity, the weight of that object, or in this case, your weight. Okay, so the force I need to use in this equation is the weight of Thomas. I have his mass, his weight, Fg, is equal to mass times gravity on Earth. Now I'm going to use 10 and round it, okay, instead of using 9.8. So we're going to get an approximate answer. If you're doing it, you're going to want to use 9.8 later on. But I'm going to say his weight is 800 newtons. I did 80 times 10. Okay, so we're going to get an approximate answer. All right, so his work would be his weight, 800 times the displacement, 4.16, and that would give me 3,328 joules. Okay, so that's his work in climbing the stairs, and now we just need to find his power. Work divided by time, divided by 63, and his power output is 52.8 watts. Unsurprisingly, it's greater than mine is because he had more work and he did it faster, which is not surprising that you guys would climb stairs faster than me. Okay, 52.8 watts. Does anybody have a question about this one? Again, if you're climbing or lifting, stairs, ladder, whatever it may be, please make sure that you use Fg. You need to apply that force up in the opposite direction. All right, how could Thomas increase his power output? Or think about yourself. How could you increase your power output if you were doing something like climbing stairs? Go faster. That's one way. What else? How else could you have more power? Sure, if you went a greater distance, sure. But let's say there's not a greater distance, it's just the school. There's one other way. Way more. Okay, yeah, you weigh more. If you had more force, okay. So now it's kind of difficult to just instantly gain weight. I mean, I guess you could sit at the bottom of the stairs and eat a bunch of snacks. But you could just carry something and that would also work. But do it faster or use more force. So carry something or try to gain a bunch of weight and do it again. Either way, that would increase your power output if you're climbing stairs. Okay, if you weigh more or if you do it faster. All right, let's try this one. A car engine has power of 120 kilowatts. If it exerts 6,000 newtons while traveling 30 meters, how much time does this take? Okay, first things first, we're going to label everything, but guys, can I use kilowatts?
Yeah.
Not if I want things to cancel. Anybody know how many watts are in a kilowatt? 1,000. Based on that prefix, you should. Kilo is 1,000. Okay, so 120 kilowatts is 120,000 watts. Okay, so I've got my power. I have a force, 6,000 newtons. I have a displacement or distance here, 30 meters, and I'm looking for time. I'm not actually looking for power. I need to fix that. I'm looking for time. Okay, I know my power equation has time in it. Work divided by time. Okay, but I don't have the work. So before I can use that, okay, I need to first find the work. Okay, so I guess I do need to use both of these equations, but I'm going to actually use this work formula first and then find the time from my power equation. So my work equation, force times displacement, I have those two numbers, 6,000 times 30 is 180,000 joules. Okay, so that is the amount of work. If I substitute and plug that into my equation over here for power, I get this. Here's my power, 120,000 equals 180,000 divided by T. Guys, my first period was doing this, and I know you guys, some of you are going to do this as well. If you have this and you're trying to solve for t, your next step is not dividing both sides by 180,000. That does not work algebraically. Okay, you have to get the time out of the denominator. Right now, this is 180,000 over time. So your first step mathematically needs to be multiplying both sides by time. Now it's on top. 120,000 times t equals 180,000. Now when you divide, you'll be isolating that variable, and now you're dividing in the right order. 180,000 divided by 120,000, that's the order they should be divided, will give you a time of 1.5 seconds. Okay, so my answer to this question is 1.5 seconds. Does anybody have a question about this one? You're going to see questions today that look similar to all of the examples that we've done in your assignment 601.4 Power Problem Set. You have the remainder of the class period to work on this, and of course you can ask for help from me or your neighbor if you need it. It's due by 11:59 p.m. tonight. You have 20 minutes left in class to work on it. The other thing that you have that's due tonight is your RA. Don't forget to turn that in. I only need one for the pair of you. So whoever's sheet you're using, that person needs to finish it up and turn it in, or you can both finish it up, but that person needs to turn it in. I don't need it turned in from everyone. I just need one sheet for the two of you. Okay, but that's due by 11:59, as is this. So go ahead and get to work. If you have questions as you're working, please let me know.